This week we're going to be covering Chapter 17, Electrochemistry. But before we begin, I'd like to let you know that next week, on April 20th, during our normal class time, the first part of it will be a test. The test will cover the last things that we've covered, March 30th, Chapter 11, the Chapters 14, 15, and 16 that we did on the April the 6th, and Chapters 12 and 16 that we did last week. At the end of the different videos that we have today of this variety, I'll be going through a review of all of the different homework assignments that you did over those times. So since the ones that were due today, April 13th, you only get credit for those, and you only get credit for any of the homework if you turn that in prior to the beginning of the normal class time. And as before, I'm always available during that class time to answer any questions. And if you got something beforehand, I usually check the online messages once a day. Hopefully we were in sync on that, and it's not more than 24 hours before I get back to you on something. But anyway, let's begin talking about electrochemistry. Now, the first thing is to review what we're going to cover today. The first is going to be a quick review of the redox chemistry that we've done before. We'll then go on to galvanic cells, electrode and cell potentials, the potential energy, free energy, equilibrium, all those different values. The typical batteries and fuel cells that we have today, corrosion concerns, and then finally electrolysis. So first of all, what we're going to talk about are the different aspects of redox chemistry and how because that's going to fit in quite well. Back when we started doing these things, we worked with the half reactions in balancing those things. And you'll see why that's going to be extremely important when we're talking about these fuel cells. So electrochemistry is the study of the interconversion of electrical and chemical energy. Chemical reactions transfer electron, chemical reactions involve electron transfer. That's one of the ways we were looking at them during all of our redox reactions. Even acid-base, if you look at it on the basis of a Lewis acid and a Lewis base, does involve electron transfer. But here, because of those electron transfers, that means that we are having a presence and flow of electrical charge. Okay? So it either can be electrons or the ions that can carry those charges. So remember back on the oxidation. Then oxidation results in an increase in the oxidation number. Copper, which would have an oxidation number of 0, going to copper plus 2, would be an increase of 2 for the copper atom, with the release of 2 electrons. So copper is being oxidized in that reaction. Reduction is when something gains electrons. Okay, so the electrons are now on the left-hand side of the equation. So silver reacting with taking on electrons makes silver metal. And so its oxidation number is being reduced from +1 down to 0. So let's go through the different steps again, just a quick review. The first thing when you're balancing a redox reaction is number 1, assign oxidation numbers. 2, you split the reaction into 2 half reactions, an oxidation and a reduction. That's a critical step. You have to split it into 2 reactions. You balance 1 half reaction. Based upon what happens there, you balance the other half reaction and combine them in such a way to eliminate the electrons. And then you also remember how you have to add the water molecules or the hydroxide ions or those things in there, should that be required. And finally, check that all of the atoms and the charges are balanced in the equation. So those are the steps for the balancing the redox reaction, and that's just a quick review of what we covered earlier. So now we can go on to galvanic cells. What this does is it's going to describe the function of a galvanic cell and how we use cell notation to symbolize the composition and construction of a galvanic cell. If you galvanize something, essentially what you're doing is you are putting you are covering it with a plate of something, right? And we'll cover the silver plating of silverware later on in the chapter. But that's the general idea. If you have a piece of copper metal, it's added to silver ions. Okay. So here, what you would be doing is you would be taking silver ions and then adding them to form silver, and you'd have copper and releasing the copper ions. And you can run this directly from just a single test tube. If you have silver metal deposited on the surface of a copper strip, okay, that's a way to essentially counterfeit money, right? You do an electric reaction to deposit silver over something that's basically just copper. Unfortunately, most of our money is that sort of thing today, if not with a nickel base, because even copper is getting to be too expensive. But anyway, copper enters the solution as the blue cupric, so that's Cu2+ ions. So you can force electrons to pass through external wires too. Okay, copper wire in an aqueous solution of silver nitrate. Both of them are happening all in the same exact cell right there. But when we're talking about galvanic cells, most of the ones we're talking about for these redox reactions occur in two separate cells. So in principle, any spontaneous redox reactions can serve as a source of electrical energy in a galvanic cell. Cells designed to take advantage of the movement of electrons, which occur during that reaction. So each one of these half reactions are compartmentalized in half cells. Oxidation occurs at one electrode, and remember that's going to be the anode. Okay. The reduction occurs at the other one, and that's the cathode. So electrons move through an external wire from the anode to the cathode, and these moving electrons are the source of the electrical energy. So, as I said, just to restate what I just mentioned, oxidation reactions occur at the anode, so the anions flow to the anode. Reduction reactions occur at the cathode, so the cations flow to the cathode. Okay, anions to the anode, cations to the cathode. Pretty straightforward. And here is an example of exactly that type of thing. What we have here is we've got a copper anode and we have a silver cathode. So the silver is flowing to the cathode, and these are flowing out into solution. You also have a bridge of sodium nitrate here, and I'll talk about that later on. This is sort of a porous plug so that the current can flow, and you get certain other things in solution here. But here you have a flow of electrons in this manner. Okay? So in this one, the copper metal dips into the solution of copper 2+ ions, and the silver metal dips into the solution of the silver ions. External wires are connected to a voltmeter, and you'll see that one of the key things here is that the energy is going to be measured in those volts. So this is the overall reaction, and this is the reaction at the anode. Copper is reacting to produce the copper +2 ions plus 2 electrons. The electrons flow then from the anode through the voltmeter to the silver cathode, and the voltmeter indicates the cell's potential. The electrons enter the silver cathode, according to this reaction right here, And so that overall, this is what happens. As oxidation occurs, a surplus of positive ions builds up at the anode, and the area near the cathode becomes deficient in positive ions. And a salt bridge supplies additional cations and anions needed to balance out these charge differences and complete the circuit. And the salt bridge is a porous material consisting of a concentrated salt solution. Most of the time it's something like sodium nitrate or potassium nitrate. Okay, single ions in each one. And the anions flow to the anode to neutralize the buildup of positive charges, but don't enter into the reaction. Cations flow to the cathode to replace the cations that are being consumed. So the flow of ions enables electrical neutrality to be achieved. Circuit is complete and the current flows. So, some of the key things here. What happens describes a galvanic cell. Oxidation is on the one on the left-hand side, and the reduction is on the right-hand side of that one. You've got a single vertical line represent a phase boundary. A double line represents a salt bridge. You don't include the spectator ions, that would be the sodium or the nitrate. Sometimes the concentration of the ions is included. So these are all the different ways in which to connote those sorts of reactions, independent of whether you actually have the two separate solutions present. But as you see at the bottom of the slide there, copper, that's the one that's being oxidized, and that is going to be on the left-hand side on this side, and this is going to be the one that's reduced on this side. Okay? So here's another example. Here you have magnesium as the anode, and you have platinum as the cathode. Now, what happens is with that cathode, you have in solution, you have Fe3 plus ions being converted to Fe2 plus ions. So this is the reaction that's taking place. This right here, the platinum cathode, just allows the transfer of the flow of the electrons so that this reaction can take place inside the solution. Okay? So that's another way in which a reaction can take place. So this doesn't have to be made of the material in which you can do it. You can have both ions in solution, where you use something like platinum that serves as a catalyst and a medium for which the electrons to flow. So compartmentalizing the oxidation reductions, half reactions, and half cells enables spontaneous redox reactions to be a source of electrical energy. In one half cell, the anode, oxidation, occurs. In the other half cell, the cathode, the reduction occurs. Each half cell consists of one electrode dipped in an aqueous solution. Half cells are joined by an external wire and a salt bridge. So this is a summary of what we've learned there. Let's go on then to electrode and cell potentials. Now what we're going to talk about is we're going to talk about the exact energy, and by calculating the potential energies, predict whether something is going to be spontaneous or not in terms of reaction. So electrode and cell potentials. In a circuit, the flow of a charge is a result of electrical potential difference. That's the voltage, okay? Electrical potential difference means voltage. So electrical potential is the ability of electric field to do work on a charge. The galvanic cell, in the galvanic cell, this electrical potential difference is called the cell potential, okay? So electrical potential is the voltage you're going to see, and that's going to be the cell potential. So the flow of electrical charge results in the difference in the electrical potentials at each electrode. Okay. So what we're going to do is we're going to stop there and continue on during the next section.